transition state for CO has been taken as 0. That is why what happens is it has a very good affinity for transition metal complexes. And then there is a general tendency that the metal carbonyls or these complexes, they follow the 18 electron rule. So this we will study in a bit. What is this 18 electron rule? So what happens here is many compounds that can be prepared from these transition metal carbonyls. Like what happens is once we prepare a transition metal carbonyls, it paves the path for the design of other new compounds. The carbon monoxide, it can undergo substitution by various ligands, and also the carbonyl group, it can stabilize the molecule whenever it is susceptible to oxidation or other decomposition reaction. So that is why this first CO ligand, it has been used for the design of new compounds, because what happens here is it can undergo different types of substitution reactions by using other ligands. Plus what happens is this CO group, it also sometimes prevents the thermal decomposition of the complexes that is associated with it. So the formula for stable carbonyl complexes that are formed in the metals in the first transition series, that has been here, it has been shown in table 5.1. Now we will just look at into this table. When we look here, table 5.1, it has been shown here. Just a minute. Okay, so we will gradually come to this table 5.1. So here we see here. This is table 5.1. So here we can see some of the ligands and the carbonyls that are attached to it. So this we will come later. So first we will define what is this metal carbonyls. Okay, so one example here has been given, hexacarbonyl vanadium. So here hexacarbonyl means CO is present in 6 in number. So that is, and vanadium is V. So the formula is VC06. So first, what the one of the most important criteria for metal carbonyls is that they follow the 18 electron rule. So but here if we look into this VCO6, it does not obey the 8 electron rule, but it is a 17 electron molecule. Now how we calculate this, we will come gradually, that for the calculation of the 18 electron rule. Then what happens here is this VCO6, then we should ask that why here it does not dimerizes, since it is a 17 electron rule, 17 electron molecule, then why it should not dimerize like we have complexes like Mn2CO10, CO2CO8. Then what happens here is, particularly if this VCO6 it forms a dimer, then it becomes V2CO12. Then each metal will have a coordination number of 7, which is not stable. That is why the VCO6 compound, it is less stable and it does not obey the 18 electron rule. And what happens is it easily decomposes at 70 degrees centigrade even to form the VCO6 minus, which is a 18 electron molecule, and it follows the 18 electron rule. So this is one exception that we come across for the metal carbonyls, that does not follow the 18 electron rule. Then coming to some of the preparation and properties of metal carbonyls. So here in metal carbonyls, as you can see, the first reaction is just by the simple addition of the carbonyls by the action of the CO on finely divided metal. Like if we take CO and finely divided nickel, the temperature is 25 degrees, that is room temperature, and 1 atm pressure, then we get tetracarbonyl nickel, that is NiCO4. Similarly, if we take finely divided iron and we pass carbon monoxide gas over it, and the temperature is maintained at 200 degrees centigrade at a pressure of 280 atm, so what we get is pentacarbonyl iron. So this is just by simply passing the carbon monoxide on the finely divided metal. So this nickel tetracarbonyl, it is a toxic volatile colorless liquids. dense, and it is highly dense. It is 6 times almost denser than air. So when there is decomposition of this nickel tetracarbonyl, then what happens is we get nickel plus 4 CO. This CO, it is liberated, and the nickel that we get, it is purified nickel. Now this process is called as the Mond process of extraction of nickel. Similarly here, the pentacarbonyl iron, it is yellow red in color, and it slowly decomposes in air, and it is very sensitive to light. So this FeCO5, when it is photolized, that means when it is subjected to light, then it gives the orange color of its dimer, that is Fe2CO9. Here FeCO5, it then, if H nu is light is passed through it, it forms the Fe2CO9. Then another method of preparation of carbonyls is called as the reductive carbonylation. So this reductive carbonylation is the most commonly used method to prepare the simple metal carbonyls. So here what happens is carbon monoxide and a reducing agent that acts on a metal oxide or a metal halide, and the respective carbonyl is formed. So what happens, how do we this reaction is performed? Here it is shown that suppose we take CrCl3 plus aluminium, that is the reducing agent, plus we have the CO and AlCl3. In presence of AlCl3 at 25 degrees centigrade, we get CrCO6. So this is called as reductive carbonylation because it employs a reducing agent. Similarly, if we take osmium tetroxide OSO4 plus carbon monoxide and at 250 degrees centigrade plus a reducing agent, that, and it will give us osmium pentacarbonyl osmium plus carbon dioxide is liberated. So this is how the reductive carbonylation process is employed to get most of the simple metal carbonyls. So other methods here of preparations, it has been shown in equation 5.10 and 5.11. So in this method, what happens is VCl3, it is reacted with 6CO in presence of diglyme, so which forms nickel diglyme plus the VCO6, which it forms the nickel diglyme VCO6 complex, which on heating with HCl and ether, it forms the VCO6. Then also WCO6, if we react it with pentacarbonyl iron at 100 degrees centigrade, we get WCO6, that is hexacarbonyl tungsten plus FeCl2. So this is how, these are some of the methods of preparation of carbonyls. So the method which depends, the most of the methods here we can see it is highly dependent entirely on the type of the metal that we are using. Supposing Fe2CO9, this is a dimer of FeCO5, and this is obtained by passing light or by the photolysis of FeCO5 in acetic acid solution. So then polynuclear carbonyls, so which means that polynuclear means more than two types, either two metals or more than two metals that are present. So that is, they such type of carbonyls, they are called as polynuclear carbonyls. So they are obtained by the thermal or by complicated decomposition of carbonylate anions in alkaline media. Like for example, it has been shown here. So we take NaCa, that is sodium cobalt tetracarbonyl, plus MnCO5Br in THF, then we get a polynuclear carbonyl. As you can see here, it is CO4 cobalt manganese CO5 plus NaBr. So since it contains both cobalt and manganese, that is why it is called as a polynuclear carbonyl. Similarly, in the second example, we can see this is pentacarbonyl iron, and it will react with RuCO12. So what happens at 110 degree, then this type of complexes is formed. So if you look into this, one is FeRu2CO12 and the other is Fe2RuCO12. So here in both this type of complexes, both Fe and Ru is present, and hence these are called as polynuclear carbonyls. Now, the one of the important feature of metal carbonyl is the 18 electron rule, or what we call it as the EAN rule, that is the effective atomic number rule. This rule was first proposed by Sidgwick, who explained the bonding in transition metal complexes using this rule. So, what happened here was the first carbonyls that were known to mankind were those of iron, cobalt, and nickel. So what, once their formula has to be applied, so this formula have was applied, the derivation of the formula of these metal carbonyls, it was applied on the basis of 18 electron rule. So this rule can also be formulated in terms of the total number of electrons that is around the metal, around the central metal atom, in which this number is usually, it is 18 electron rule, means the number of electrons around the central metal atom should correspond to 36, 54, or 86. That is, it will correspond to the atomic number of the noble gases like such as krypton, xenon, and radon. So once they usually correspond to these atomic numbers of the noble gases, then we say that they obey the effective atomic number rule. Because the pseudo-noble gas valence or cells of krypton, xenon, radon, they contain 18 electrons. It is simpler just to count the valence cell electrons. That is, to understand the effective atomic rule, we will just calculate the total number of electrons, valence cell electrons, that is present in the central metal atom. So EAN is referred to as the effective atomic number rule. The complexes of transition metals with pi acid ligands and their organometallic compounds, they obey the EAN rule. The central metal atom, it appears to have acquired the configuration of a noble gas. The total number of electrons which the metal ion appears to have around itself is called as the EAN. If it is 36, it follows krypton. If it is for 54, it is similar to xenon, or 86 radon. So now when we can say that the metal achieves an outer electronic configuration of totally fulfilled shells, that is, the D should be 10, NS2, NP6, then there will be 18 electron valence electrons in the outermost configuration. So this is how we actually calculate the total number of electrons that is present in the valence cell configuration of the metal. So the transition metal complexes that we have studied, they are some classical complexes. They contain the metal in oxidation states of +2, which involve mostly N or O donors. So this is how, what we say is, when bonds are formed, then the orbitals should match in energy. That is what we have studied is, they will have similar energy. Now this is noted in the middle of part of the transition series and for metals in low oxidation state. So increasing the oxidation state, it changes the slope of the binding energy versus the atomic energy curve. So what happens here is, the EAN rule does not hold good for very positive oxidation states. So like particularly we have elements like rhodium, palladium, iridium, platinum. They have the very least tendency to be 6 coordinated, and they form mostly 4 coordinated complexes. So in most cases, the maximum coordination number that we come across is 6. And if each ligand donates a pair of electrons, then they must have D6 configuration to follow the 18 electron rule. Now when we have the metals with D8 system, they need 5 electron pairs, and the expected geometry is, since the 5 electron pairs is needed, the expected geometry is TBP, or square pyramidal with D10 configuration. So here this rule particularly predicts the geometry and the types of mechanism that is based on the bonding here in the metal carbonyls. So now we will come to how to actually calculate the electrons that is present in the complexes. So first step is, we must count the number of the electrons that is present in the valence cell of the metal atom. We will consider the metal atom. Suppose we take nickel tetracarbonyl. Then nickel is the central metal atom here. We will first write down the electronic configuration of nickel, and then we will count the number of valence cell electrons present in nickel atom. This is the first step. The second step is that we will check the number of electrons that the ligand donates to the central metal atom. So here, in supposing we are taking nickel tetracarbonyl. So carbonyl means CO, and each CO, it is should be always remembered that each CO ligand, it contributes two electrons. Now supposing in nickel tetracarbonyl, that is NiCO4. So here CO is present in four numbers. So now we know that one CO, it donates two electrons. So in nickel tetracarbonyl there are four CO. So that is why the total number of electrons that is donated by the ligands is equal to 4 into 2, that is equal to 8. So this is how we calculate the number of electrons that is donated by the CO ligand. Now in the third step, if there are any other ligands present, then we will also check the number of the electrons that are contributed to them. Now in nickel carbonyl, there is only the carbonyl ligand. So hence we'll just calculate the number of electrons that is contributed by the CO. Supposing in a metal complex, there is a MM bond, like in binuclear complexes, suppose we have Mn2CO5. Now in Mn2CO5, there is a metal-metal bond, that is there is a Mn and Mn bond. So this type of metal-metal bonds, they donated how many electrons they are donating, that has also that needs to be added. Now once we have look calculated the all the electrons that are donated to the central metal atom, we will now add up all the electrons, and this will give us the value of the effective atomic number. So we will look for an example below. Now the metals which has odd atomic numbers, they cannot satisfy the 18 electron rule just by simply addition of the CO ligands, because if we the metals with odd electron numbers, they will provide a odd value. So that is why there are several options by which these metals, that is the metals with odd electron number, they can be satisfied. Now here the simplest one is by addition of one electron, as you can see here, to form the carbonylate cation, like here MCON minus. So there are some stable compounds with electrons other than 18. So in such compounds, the factors such as the CFSE, that is the crystal field splitting energy, the nature of the metal to carbon bonding, they all contribute. These are the factors that also contribute to the stability of the compound. Some of the metal carbonyl compounds of D, they also obey 16 electron rule. Now we talked about VCO6. It has 17 electrons, and that is why it is called as a 17 electron species. So how it will form the 18 electron rule? So it will accept an electron and it will form the VCO6 minus carbonylate anion. This cannot polymerize that to form a dimerize actually, because it is highly unstable in nature. So these are some of the process, one method by which a metal can follow the 18 electron rule. Another example that we can talk of is the MnCO5. So this MnCO5, it has 17 electrons, but this does not accept an electron. Rather, MnCO5, it forms a Mn double bond. Sometimes it forms MnCO5 minus, or we can see that it dimerizes to form the Mn2CO10 molecule. So here one example for the Mn CO5 minus, it has been shown. So here for manganese, the outermost electron is 7. We know that one CO, it contributes 2 electrons. So 5 CO, it will contribute 10 electrons. So now the charge here, since we have taken MnCO5 minus, then since outside there is minus charge, so this charge, it becomes 1 electrons, and therefore the total electron count becomes 10 plus 7 plus 1, that is 18. So similarly we will again consider another case, CO4 minus. So cobalt, there are 9 electrons in the valence shell. We will always first write out the valence shell electronic configuration of the metal. So the valence shell electronic configuration for metal, it gives us 9 electrons. So once it is, then for 4 CO molecules, there are 8 electrons, and since there is a minus charge here, it gives us 1 electron. So the total electron that comes is 18 electrons. So this is how we count out the 18 electron rule for different type of metal carbonyls, and this is particularly for the metal carbonyls having a negative charge. Then we will now calculate the metal carbonyls. We will apply the effective atomic number rule for the dimeric species. For example, we will take the case of Mn2CO10 and CO2CO8. So first we will start with Mn2 and CO10. Now for 1 Mn there is 5 valence shell electrons. So since 2 Mn is present, since 2 Mn there is 14 electrons. There are 10 CO. So here, since 10 CO, so the total number of electrons that comes is 20. Now we also have a metal-metal bond, that is Mn-Mn bond, and we know that metal-metal bond will contribute 2 electrons. So that is why after adding this, that is 14 plus 20 plus 2, it becomes 36. Since it is a multiple of 18, it also follows the effective atomic number rule. Then coming to CO2, CO8. So one CO, it has 9 electrons, 2 CO, it forms 18 electrons. Then cobalt, then 8 carbonyl, it contributes 16 electrons. We also have a metal-metal bond, that is cobalt-cobalt bond, which gives 2 electrons. So upon adding, we also see that it follows the effective atomic number rule. So this is how we can calculate the total number of electrons. Now here in a back, this is a back calculation process. Here we can see, we can use this 18 electron rule to find out the value of n. Suppose we don't know how many carbonyl ligands they are attached to the central metal atom, we can follow a back calculation process and we can actually predict the molecular formula of the compound. So let us use this compound cobalt 2 carbon monoxide, or the carbonyl ligand N. So what we will do is, so we will first look into the central metal atom, that is cobalt. So cobalt 2 number are present here, so that is why the electron that is contributed is 18. Now here carbonyl ligand is present in n number. So we know that one carbonyl, it contributes 2 electrons. So n carbonyl, it will contribute 2 into n. Then in the third part, we see that CO2 is present, that is cobalt-cobalt bond is present. Since a metal-metal bond, it will give us 2 electrons, so we will write 2 electrons. Now we will consider apply the 18 electron rule, that is we will add up these electrons, that is 18 plus 2n plus 2, it becomes 36. So once from this, solving this formula, we get that n is equal to 8. So the molecular formula for this compound or the carbonyl complex becomes CO2CO8. So this is one back method of calculating the number of carbonyl ligands that can get attached to the to the central metal atom. So this is how effective atomic number, it plays an important role. Now here we just talked about carbonyl, and we know that the neutral carbonyl, it contributes the CO ligand, it contributes 2 electron to the metal. But there are also other ligands which contribute different number of electrons to the metal. Like for example, thiocarbonyl, that is CS, it also contributes two electrons. Phosphine, that is PR3, to amine, it gives us 2 dinitrogen, also 2 dihydrogen, 2 electrons. Alkene gives us 2 electrons. Alkyne gives us 2 electrons. Isocyanide, that is CN, it gives 2 electrons. But if we have a bent nitrosyl, it gives us 3 electrons. But if we have a linear nitrosyl, it gives us 1 electron. So then the halogen, hydrogen, alkyl, acyl, aryl, the amide, phosphide, alkoxide, they all contribute 1 electron to the central metal atom. Then carbene, if it is in alkylidene, that is if it is equal If it is present in M double bond Cr2, it will contribute 2 electrons. But if it is present in M double bond Cr, it will contribute 3 electrons. Then here comes cyclopentadienyl. If it is monohapto, then it contributes 1 electron. But if the cyclopentadienyl ligand is present in eta 5, that is pentahapto, then it will contribute 5 electrons. For benzene, it is 6 electrons. For eta 7 cycloheptadienyl, number of electrons is 7. And for cyclooctatetraenyl, the number of electrons is 8. Now, if there are any bridging ligands like of this type, MCOM, they contribute 2 electrons. If there is halogen bridging type MXM, they contribute 3 electrons. And these are some of the other possibilities of alkyl, amide, phosphide, alkoxide. They all contribute 3 electrons. So sometimes so these are some of the contributions that we have to remember while we solve the number of electrons for our complexes. Now, these are some of the details of common ligands that are found in organometallic compounds. So here, the hydrogen, we know that the formal charge for hydrogen, it is 1, and the number of electron donated is 2. Suppose we have the halogens, that is fluorine, chlorine, bromine, and iodine. The charge is -1, but the number of electrons that is donated by these ligands to the metal, it is 2. Then we have cyanide. Here the charge is -1 and the electrons donated is 2. Suppose we look into the nitrosyl ligand or the carbonyl ligand. If we talk of, the charge is 0 on the carbonyl ligand, but we know that the electron that is donated by carbonyl ligand is 2. Similarly, nitrosyl, that is NO, the charge on this ligand is 0, but the electrons donated by this ligand is 2. So these are some of the factors that we need to remember. Now, there are several exceptions to the 18 electron rule. Sometimes the molecules with 16 valence electrons, they are also stable, and they have been found to be, in certain cases, they have found to be more stable than the 18 electron molecules. However, such cases, they have been found for the true for the bottom right corner of the transition metal series, that is for rhodium, palladium, iridium, and platinum, which do not have an inclination to form 6 coordinate complexes. Rather, they can definitely form 16 electron molecules. So these 4 particular elements, rhodium, palladium, iridium, and platinum, they also form 16 electron complexes, molecules, and which are highly stable in nature. Now these type of complexes, they are found to have, they have D8 metal atoms, and they are square planar in nature. They may also have D10 metal atoms with 3 ligands, and they mostly have trigonal shape. Like for a D8 system, that is either rhodium plus or iridium plus, PD2 plus or PD2 plus or PT2 plus. Here one complex example it has been shown. These are they are stable in nature, MD4 type, and you can see, since it is MD4, they are square planar in nature. They are not octahedral. They form 4 coordinated complexes. They do not form 6 coordinated complex. So if you look into here, iridium, so iridium here, this is the central metal atom. PPH3, 2 PPH3 are there, 1 CO and 1 Cl. So overall, the total electron count here, it is 16. Similarly, in another case, for a D10 type, where we can see for a platinum complex, this is a D10 type, it forms a trigonal bipyramidal trigonal shape. So, and this is also a 16 electron molecule, and it does not follow the 18 electron rule, but it is still stable in nature. So these are some of the exceptions that we find. Then some intermediates in reacting organometallic compounds, they do not have been confirmed, like PTCPH2, a 14 electron complex has found to exist, but this is very rare. Now the question is, why the 16 electron complexes are stable in nature, since we have the effective atomic number rule for 18 electrons. So how are these 16 electron complexes, they are stable in nature? So let us, to understand this, we will consider M as the metal and D as the ligand. So in D8 configuration, square planar is mostly for the D8 square planar complexes are formed. So the 16 electron MD4 complexes, they have similar chance to 18 electron MD5 complex. So there is a possibility that rather than becoming D8 and square pyramidal, they can form D8 and 10 ligand electrons to form 18 electron rule. But the MD5 here, it is more stable than the MD4 for a D8 metal atom. So what happens is the D8 metals, they can form stable 16 electron square planar complexes, but they are easily oxidized to form the D6. So similarly, the D10 tetrahedral complexes, but they may exist as MD4, but due to the ND and NP mixing, they are not much stable. So that this is the why 16 electron complexes, they are found to be stable in nature. So there is another ligand that we call it as the nitrosyl ligand, or that is NO. So we know that this NO is an odd electron molecule, so which possesses the nitrogen here, it possesses a lone pair but also one electron in the pi molecular, that is pi star MO. So here we treat NO as coordinated, that is mostly NO is treated as NO plus, where the extra electron count is, it is counted with the metal and other ligands. So other conventions, they treat NO as a 3 electron donor, but here in our convention here we see that NO, we use that NO plus is similar to CO, Cn minus and N2. These are all isoelectronic species. So the NO plus ligand in the complex, it will involve its pi molecular orbital with its metal d pi atomic orbital to form the residual metal nitrosyl. So now we will consider the electron counting in NO complexes. Here two examples have been shown. So here it is a nitrosyl and a carbonyl complex, that is MnCO4MNO. So this compound is named as tetracarbonyl nitroxyl manganese. So in this compound NO plus, it contributes one sigma pair. One sigma pair means two electrons. Then the 4 carbon here, in this case it contribute one sigma pair. So then Mn minus, here it contributes 4 pairs. So overall we have 9 sigma pairs, so which indicate 18 electron rules. This is how we do the calculation when we have NO and the CO. So another example is dicarbonyl dinitrosyl iron. So 2 NO plus we have, it is 2 sigma pair, 2 CO, it comes 2 sigma pairs, and Fe2 minus, it forms 1 pair. So total we will there are 18 electrons. So now this you can calculate also by the conventional method, and this is how the calculation is done. So the ligand here in figure 5.2, this is a cyclopentadienyl ligand. So this cyclopentadienyl ligand, we know here a hydrogen and the eta 1 structure, that is the monohepto, here it is shown here, and it is how the pentaheptocyclodienyl ligand, here it is shown in the figure 5.3. So this is pentahepto, it means it is eta 5. So how? So for the structure of the, if we attach an iron to this, and here the structure of this FeCO2 eta C5H5, that is bihepto, and the monohepto cyclopentadienyl ligand, it has been shown like this, and then the further calculation of electron pairs has been shown here. Then these are some of the examples of calculations of complexes of using the effective atomic number rule. So now we will study the properties and structure of different metal carbonyls. So here most metal carbonyls, they are volatile solids, but FeCO5, RuCO5 and osmium pentacarbonyl, they are nickel tetracarbonyl, they are all liquid at room temperature. So most of the discussed ones, they are soluble in organic solvents. The different carbonyls, they have varied reactivity, like the CO2, CO8, it reacts at ordinary temperatures. But FeCO5 and NiCO4, they are easily oxidized. Their vapors form explosives with air. Here CrCO6, molybdenum CO6 and tungsten CO6, they do not react unless they are heated. So this is how about their reactivity. So some stable binary carbonyls, it has been shown here. VC in the first transition series, as you can see, VCO6 is a black solid and it decomposes at 70 degrees centigrade. But the CrCO6, it decomposes at 130, whereas if you look into nickel carbonyl, it decomposes at 45 degrees centigrade, 43 degrees centigrade. So some of the here the properties of the first, second and third transition metals which form carbonyls have been shown here in this table. So all metal carbonyls, they are solid. Exceptions are some of the mononuclear carbonyls. So of the iron and nickel, all mononuclear carbonyls, they do not have any color, but the polynuclear carbonyls, they have color. So as the number of atoms, it increases in the polynuclear carbonyls, then their color, it becomes dark in nature. So the following are some of the structures. So here nickel tetracarbonyl, it has a, we know it has a tetrahedral shape. Here it has been shown here. So in this nickel CO4, there are three NiCO bonds, and the bond length for Ni and C, it is 150 picometer. The bond length of CO, it equals to 115 picometer. So then here, if we look into FeCO5, here in the figure 5.10b, it has a TBP structure. So here the axial and the equivalent bond lengths, they are marginally different. So they are, and they have been proved by the X-ray diffraction studies. So if we look into chromium CO6, it has a octahedral structure, and this will have the CO group, it brings electrons in pairs. It is clear if this chromium metal, it has an odd number, so therefore the mononuclear species, it will have an unpaired electron, and since it contains an unpaired electron, it is paramagnetic in nature. So we discussed about mononuclear carbonyls. So now we will talk about binuclear carbonyls. So binuclear carbonyl means there is a metal-metal bond. That is, they are characterized by the presence of metal-metal bond. The CO ligand, it can fulfill three different structural functions and has three different bonding modes that is recognized by a characteristic stretching frequency. Now where does this stretching frequency comes from? This stretching frequency comes from the infrared spectroscopy, or we call it as FTIR. So this stretching frequency, how they were first identified by the FTIR spectroscopy, and they have been in neutral complexes. The free CO, it has been found in 2143 centimeter inverse, and if the CO, they are present in the terminal position, that is 2122 1850 centimeter inverse, and if there is doubly bridging, then if they are found in the peak, it comes in the region of 1850 to 1750, and for triply bridging there is 1730 to 1620 centimeter inverse. So when we take the IR of a this binuclear carbonyl, if we see the presence of its peak in this region, then we can know the type of the carbonyl, metal carbonyls that is present in our compound. So now this is a useful distinction, but there are many cases, but this we can identify the terminal carbonyl groups that is present in the binuclear carbonyls. Now let us take the example of a binuclear carbonyl, that is Mn2CO10. So this has a structure which composed of two staggered MnCO5 units, and they are joined together by Mn bond. So this is one unit of the MnCO5. This is the second unit of the MnCO5. So these two units, they are held together by the Mn bond that is shown here. So this bond distance between Mn and Mn, that is between the two metal atoms, is 279 picometer, and this Mn atom, each Mn atom is linked to 5 other CO groups. So there is no bridging carbonyl groups. These are just attached by the metal-metal bond. There is no, the metal-metal, they are not held together by any carbonyl groups. So here we can, this structure is simplified and it can be shown like this. This is metal-metal and it has been shown like this. Then coming to another binuclear carbonyl, that is Fe2CO9. So what is this Fe2CO9? This has both bridging and terminal CO groups. So if we look into this Fe, these are the terminal groups for the CO. Here each Fe, it is linked to three bridging groups, that we can see. For each Fe there are three bridging CO groups, and they are held together by three terminal CO groups, which by a coordinated bond. So here for this Fe there are three, you can see this is one CO, this is one CO, and this is one CO. So here this Fe, that is held together to other three terminal CO groups by coordinated bond. And then there is another bond, that is the metal-metal bond, that is present here. So this is how the Fe2CO9 has its structure. Then another example we will talk of, that is CO2CO8. So it is a very orange brown crystal solid. It is soluble in alcohol, ether, and it is in CCl4. So it has a bridge structure. So if you look into the structure, so what happens here is, so each CO, it has three terminal CO groups. So the cobalt here, three terminal carbonyl groups are present. Then also we have two carbonyl, two bridging carbonyl for the cobalt groups, and in addition to that there is a cobalt cobalt metal bond. So as this arrangement, there is also an isomer possible for this type of arrangement. So that is, here it is shown in figure B. So the two isomers of CO2 CO8, they are in equilibrium structure, they are in equilibrium with each other, and this has also been confirmed from X-ray spectroscopy. So now you can calculate the total number of electrons for the both the cases. So in the first case, as you can see, the cobalt, it contains a single cobalt molecule. We will consider it contains 9 electrons. There are three symptom bridging cobalt, that is for 6 electrons. We have two in this side, there are two terminal carbonyl ligands, so that gives us for the two carbonyl ligands we give 2 electrons, and one CO, that is 1 electron. So overall this is 80 electrons, and similarly you can calculate this. So they both CO2 CO8, they follow the 18 electron rule. Then the more complex polynuclear carbonyls, and they have been discussed in the later sections, that the complex carbonyls, they are called as metal clusters. Then coming to bonding in carbonyl compounds. So the nature of the bonding between carbon monoxide and transition metal, it is very interesting in nature. So this bonding is particularly the reason why transition metal carbonyls, they are found, they are very stable in nature. So in figure 5.14, first we will look into the MO diagram, that is the molecular orbital diagram for CO. So here in this figure we see this part is for the carbon atom, this part is for the oxygen atom, and in between it shows the combination of the atomic orbitals to form the CO molecule. So first we will write out the electronic configuration of C, that is 1s2, we will neglect it, and since for carbon it is 2s2 and 2p2, and for oxygen it is 2s2 and 2p4. So as you can see, the orbitals of the carbon atom, they are placed higher than that of the orbitals of the oxygen atom. This is why, because of the energy. The C atom, the orbitals of the C atom, they have higher energy than that of oxygen. That is why the 2s of the carbon is placed higher than the 2s of the oxygen. So now we can see, combine these different type of orbitals to form the CO molecule. So here the 2s will combine with the 2s of carbon, will combine with the 2s of the oxygen to form the 2 sigma orbital and the 2 sigma star orbital. And then again the 2p, it will combine with the 2p of O to form the different types of orbitals, and this is how the molecular orbital diagram of CO it looks like. So here, particularly for the CO molecule, the HOMO is sigma 2p, that is derived from the high energy 2p carbon and oxygen orbitals. The lowest, uh, that is the LUMO, will be the pi 2p star antibonding orbital. So as a result, here oxygen it contributes the from this is just the assumption of this HOMO and LUMO, they can be made from by looking into this diagram. So from this diagram, it is seen that the bonding molecular orbitals, they are fully occupied and they result in the triple bond in the formation of the CO molecule. But there is also one lone pair that is available on the carbon atom, which is presented to the metal during the metal carbonyl processes. Also, the predominant contribution, it comes from the 2p atomic orbitals of carbon, so that what happens is the approximate steps of these orbitals, it has been shown in figure, we will go there in figure 1.5.15. so this donation, the electron, because of this type presence of the lone pair, then and the other contribution of the electrons to the metal, this arrangement here that is shown in the molecular energy level, it helps in the formation of the metal carbonyl. So the metal atoms that are present in metal carbonyls, they have low oxidation states, so they may be negative, zero or positive. So then how can we say that the metal carbonyls, they remain stable in such low oxidation state? Then to understand this, it is due to the bonding effect which involves the sigma bond between the metal and the carbon. So how is this sigma bond formed? This sigma bond is formed by the overlap of sp hybrid orbital of carbon and a vacant orbital of the metal. So here the sigma bonding, it has been shown. So the sp3 hybrid orbital of nickel in NiCO4 and the dspt3 hybrid orbital of FeCO5, they have this type of bonding. So here this is the C, that here this is the orbital of the CO, and this is that of the metal which donates the electrons, and you can see how the sigma bond is formed. This sort of bonding, here it has been CO M sigma bond and MCO pi back bonding, here it is shown. So now, if in free carbon monoxide, the electrons are polarized in the direction of the more electronegative oxygen. That is, if we have look into this molecule, we know that oxygen is more electronegative. That is why the electron, it is pulled towards the oxygen. But whenever the metal gets attached to it, it reduces the polarization in the CO bond because it attracts the bonding electron. So the electrons in the positively charged complexes, they are more equally shared by the carbon and oxygen. So as a result, there is a strong bond, and so the CO is very, the stretching is very higher in energy. Simple carbonyls, they contain CO terminals which bonds through C and not O, and we will it should behaves as an electron pair donor and acceptor. The sigma donation from ligand to metal and pi back donation from metal to ligand, they are together, they are known as the synergistic effect or synergic in nature. The spectroscopic study, it has found that CO is a part of the molecule, but polynuclear carbonyls, they contain bridging CO. So in carbonyls, the sigma bonding is reinforced by additional sigma bonding, which stabilizes complexes and very low oxidation states of the metal. Many carbonyl compounds have metal in zero oxidation state. Suppose in NiCO4, in NiCO4, the oxidation state of the metal, that is nickel, it is zero. The very low oxidation state, they are not found with sigma bonding ligands such as H2 or NH3. These are only possible when CO is taken. So CO is a very good ligand for formation of different type of complexes. We'll just take a break of 5 minutes and again resume with the important reaction of metal carbonyls. So we'll start with some of the important reactions of metal carbonyls. So this is a generalized of reactions of chemical reactions of the various metal carbonyls that react with certain reagents. So for example, FeCO5, when it is heated with an alkali followed by oxidation with MnO2, it gives the trimer, that is the Fe3CO12. So in the first case, FeCO5, it is reacted with sodium hydroxide followed by treatment with MnO2, it will give Fe3CO12. Then the most important chemical reaction is the formation of carbonylate cation. We see the formation of the carbonylate anion by the addition of alkali. So, like for example, we have talked about VCO6. Since VCO6 is a 17 electron species, it becomes an 18 electron species by forming a carbonylate anion. That is, it forms VCO6 minus and it is stable in nature. So here, some of the reactions it has been shown here. Suppose FeCO5, it reacts with sodium hydroxide to form the corresponding carboxylic acid, and then it under further reacts to form sodium hydroxide and hydrido anion. Here FeCO5 plus NaOH, it forms Na2CO3 plus H2O followed by the NaHFeCO4. Again FeCO5 reacts with Na, this Na2H FeCO4. So further reduction, the further formation of carbonylate anion, it takes place, the nucleophilic attack takes place, and it forms Na2 FeCO4 plus CO. So this is some of the addition of alkali or the reduction reactions. The formation of carbonyl hydride takes place by reaction of metal carbonyls with hydrogen. Suppose we react hydrogen with Mn2CO10, then it forms the HMnCO5. These are called as the hydrides, or we call it as the carbonyl hydrides. Suppose we react cobalt carbonyl CO2CO8 with hydrogen, it forms H cobalt CO4, that is the carbonyl hydride. So this is by just reacting the carbonyl with the hydrogen, we can say then they form the carbonyl hydrides. Then the formation of carbonyl halide also takes place by the reaction of metal carbonyl with halogen. Suppose we have FeCO5 and it reacts with a halogen, that is X2, any halogen, it forms the carbonyl halide, that is FeCO4X2 plus CO. So here in this equation, that is in equation 5.26, the halogen, that is bromine, here it reacts with Mn2CO10 and it breaks the Mn-Mn bond, resulting in the formation of a carbonyl halide, but it is of the formula MnCO5Br. Similarly, CO2, CO8 and nickel tetracarbonyl, they decompose in presence of halogens, the forming the halides. That is, the CO2, CO8, it breaks the metal-metal bond here breaks, and cobalt halide is formed, plus carbon dioxide monoxide gas is released. The nickel tetracarbonyl, it reacts with bromine to form the NiBr2, and similarly CO is released. So that there is other chemical reactions that includes the displacement of the carbonyl group by other ligands, which are actually called as the substitution reactions. Suppose we take PF3 and it is reacted with tetracarbonyl nickel. So in this case, what happens here is 2CO, they are substituted by 2PF3 groups. Even in the case of NiCO4 plus the isocyanide groups RCN, in this case the 4CO are released and the CNR, they get substituted. Similarly, for Mn2CO10 plus PR3, what happens here is the reaction, it breaks the Mn-Mn bond and it forms the carbon monoxide is released. Here MnCO4PR3 it is formed. So these the by other ligands, they substitute the CO ligand and sometimes they also break the metal-metal bond. Now, when we react a carbonyl with a nitrosyl, then with the NO group, then a nitrosyl is formed. As you can see, FeCO5 plus 2NO. It forms FeCO2NO. That is both CO and nitrosyl. Both carbonyl and nitrosyl group are present. Even for CO2, CO8, it reacts with nitrous oxide to form the cobalt carbon monoxide 3 nitrosyl oxide plus 2 CO. So this is how the formation of nitrosyl takes place with NO. Then comes the action of heat on different types of metal carbonyls. So here FeCO5, it breaks to form Fe plus 5CO. But if we have Fe2CO9 and the toluene is taken as a solvent, it forms FeCO5 plus Fe3CO2 12. So again Fe2CO9, if it is heated at a lower temperature of 50 degrees centigrade, it forms the trimer, that is Fe3CO12. And nickel tetracarbonyl at 180 degrees centigrade, it decomposes to nickel plus 4Cu. So different type of metal carbonyls, they show different properties upon heating. Then coming to the vibrational spectra of metal carbonyls. So what is this vibrational spectra? This is mostly studied by infrared spectroscopy, or we call it as the IR spectroscopy. So vibrational spectra, the infrared spectroscopy particularly, it utilizes the interaction of the infrared with our molecules. So here mostly this spectroscopy, it studies the different types of vibrations that a molecule encounters when the infrared light it falls upon it. That there are different types of vibration in a molecule, that we call it as the symmetric stretching, asymmetric stretching, bending, the in plane bending, the out of the plane bending, the rocking, scissoring. There are so many types of vibrations that occur in a molecule. So for particularly here, and those are all the vibration, they are captured at different frequencies for, and that is studied by IR spectroscopy. So the vibration spectra, here we will only concern about the vibrational spectra of the metal carbonyls. So for particularly for metal carbonyls, the CO groups, they have two type of stretching modes. One is the symmetric stretching and other is the asymmetric stretching. So in the symmetric stretching, as you can see here, the stretching is pulled in equal directions. But in the asymmetric stretching, here we see the stretching or the indication of the arrow, that is in the opposite direction. So this is how we differentiate between a symmetric stretching or the symmetric vibration mode or the asymmetric stretching. Now, since both these mode, they have a result, they change the dipole moment of the molecule. That is why they are both IR sensitive and Raman active. So we know that a molecule can be IR sensitive or because they have there should be a change in their dipole moment. Now for example, we talk of carbon dioxide. Carbon dioxide is a linear molecule, and here the net dipole moment is zero. So that is why carbon dioxide is not sensitive to IR or Raman. But here in the metal carbonyls, the CO group, we can see there is, because of this type of stretching, there is a resultant dipole moment in the molecule, and that is why the CO, the metal carbonyls, they are sensitive to infrared spectroscopy. So here a mononuclear pentacarbonyl, it can exist both in square pyramidal and trigonal bipyramidal geometry. So after performing the IR spectroscopy, then we can actually provide the type actual geometry of the molecule. So here it gives, this IR spectroscopy also provides evidence for the possibility of the synergy effect. Then coming to bonding and structural elucidation of carbonyls. So IR is particularly useful to understand the type of bonding and the determination of the geometry of carbonyl compounds. So the CO bond order and the frequency, they are fixed, but when they are present in different environment, the carbonyls, then the stretching frequency, it decreases, it differs. Like it has been shown that the order has been shown that the free CO, the stretching frequency is greater than that of the metal carbonyl cation, neutral metal carbonyl, and which is greater than that of the metal carbonyl anion. Like the stretching frequency of the carbon oxygen, it has been found in 2143 centimeter inverse in the gaseous state. but the vibration frequency in the carbonyl compound they found to be in the range of 2100 to 1700 centimeter inverse. That is how the environment it affects the stretching of the CO ligand. So we can now, we will, with the use of this IR spectroscopy, we will assign the structure and geometry to different molecules. So so we will, for example, we will look at into the case of nickel, cobalt, and iron. That is here it is given in table 5.6. So here, this is the IR spectrum. In the figure 5.17, you can see this is the IR spectrum of the carbonyl region for FeCO5. So we'll go gradually to this. The central metal atom here in nickel, cobalt, and iron, they have 8d electrons. So however, the effective nuclear charge, we know that they differ from iron to nickel. So then the residual negative charge of the metal it is greater for iron than for the nickel. So because the negative charge increases, the metal has a higher density to give away, and so the back bonding is increased. So as a result, the electron density in the pi star will be increased, and the bond between carbon and oxygen it will weaken and vibrate at a lower frequency. So the infrared stretching frequency of isoelectronic and isostructural species like NiCO4, COCO4 minus, and iron tetracarbonyl 2, it has been shown here. So here in this table we can see NiCO4, the geometry is tetrahedral, and the stretching, the IR, it is active modes in A1 and A2. So and they are observed, the frequency it has been observed in this range. So this is how particularly for FeCO5 the IR active mode is A2 dash, and here you can see these two peaks, the A2 and E peaks that is associated for IR. So what happens here is the advantage of using IR spectroscopy to characterize carbonyl complexes is that there are a few observations in the 1800 to 2200 centimeter region. So the frequency of this observation it can give us the amount, the bond length of the carbon oxygen bond. For example, FeCO5, we refer to the D3H character table, then we can see that the vibrational mode has only one non-degenerate one and the rest are doubly degenerate ones. So if we look into the symmetry point, and then we can assign the CO stretching frequency to the metal carbonyls that has been shown here. Now we should note that the CO stretching frequency it is very sensitive to the electronic environment around the metal. So in a metal carbonyl, the high electron density it is localized on the metal. So there will be an increase in the extent of the back bonding and it will reduce the electron density. So thereafter, electron density in the pi star orbital it increases. So the bond order decreases and the bond length also increases, causing a decrease in the CO stretching frequency. So if we look into NiCO3 PME3, here the carbonyl stretching is observed at 2064 centimeter inverse. But for NiCO3 PPH3, it is 2069, and if we have NiCO3 PF3, it is 2111 centimeter inverse. So among the three complexes here, the methyl group on the PME3 they show a, we know that they show a positive, that is plus I effect. So the electron density will be towards the metal. Here the back bonding it increases and the MC bond also increases. So therefore a weak CO bonding it results and the infrared stretching takes place at a lower region of 2064. But when we consider PF3, here it has the electron withdrawing fluorine group that is attached to it. So here the back bonding is not increased, the CO bond it remains stronger and the IR stretching is observed at a higher frequency. So now let us look at what happens the IR stretching frequency in polynuclear carbonyls. So let us take the example of neutral carbonyls where the IR stretching frequency they are in the range of 1800 to 1900 for bridging CO and 1950 to 2150 for terminal CO. For example, in the case of CO2, CO8. So here particularly for this case, various types of bands have been observed here at 1857, 1886, 2001, 2031, 2044, and others. So how do we explain the presence of these types of bonds, these types of peaks in different places? So here from particularly the CO bond ends. So there are different types of the stretching frequency. They can be found, particularly they can be assigned to the terminal or the bridging CO. Even the axial positions and other stretching frequencies, they can be considered. So from the above studies, we see that the metal carbonyl stretching frequency, it increases with the as the metallic state oxidation state decreases. This is a general observation that it has been found that as the oxidation state of the metal increases, then the metal carbonyl stretching frequencies it decreases. Here, as we can see, for MnCO6 it is 416, for chromium CO6 it is 441, and for vanadium it is 460. So thus the conclusion we found that the effect of formal charge, positive charge on the metal, there is no change in the strength of the sigma bond, but only the oxidation state of the metal, it highly influences the stretching frequency. Now, while obtaining an IR spectra of a metal carbonyl, it is always taken in a vapor phase, or mostly it is dissolved in solvent. Here, why this is done? This is done because the medium also it affects the peak position. So also if we take the IR is taken in a solid phase, that is using a KBR pellet, then mostly here it is actually advisable to take IR of the metal carbonyls in the solid state if it is present in a solid. So here we will look at some simple IR spectra of certain molecules. Here in figure 1.5, the IR spectrum of Fe2CO9 it has been shown. So we could see there are strong bands here. There are two strong peaks are present, and here one strong peak that is present. So here it has both. This corresponds to both the terminal and the bridging carbonyl groups, and this type has been also been confirmed from the XRT studies. So in the second case, we will talk about the IR spectrum of Fe2CP2CO4. So here we can see there is a sharp peak at 2000 here in this region. There is also a sharp peak here, and here we can see three different sharp peaks. So here these two peaks they are assigned to the, here you can see these two regions they are assigned to the terminal CO here, and this peak it is assigned to the CO, the bridging CO. So that is how this IR spectrum it also shows that the bridging CO and the terminal CO they are present in Fe2CP2CO4. However, this is if we look into the structure of Fe4CP4CO4, this the number of the IR spectrum here there is many, because we have different type of stretching frequencies for this type of complexes. So here in figure 5.2 they have summarized in the number of type of carbonyl stretching bands that we can find. So suppose we have the carbonyl group of the type MCO5 and one ligand, the number of expected new CO stretching frequencies is 3. If we have a C2B point group for a particular type of carbonyl ligand, the number of the peaks observed in IR spectra is 4, and this is how some of the types of expected frequency has been shown here. So a more symmetric molecule, if we take a symmetric molecule, it will have less number of bands. This is from group theory. This deduction, it has been come from group theory that we will study later. Suppose the trans L2MCO4 has more symmetry elements than those in the point group C2B. So the cis compound here that is shown, it has 4 infrared active bands, whereas the trans compound it has only 1. So the symmetry of the molecule reduces as the ligand is asymmetric. The symmetry around the metal lessens and weakly active bands appear here. The infrared spectra of the carbonyl stretching of two metal carbonyl complexes, here it has been shown. This is the cis and this is the trans for the same part. So as we can see the variation for the cis part, for the cis molecule and also for the trans molecule, and this is because if we look into the symmetry of this molecule, that also affects the nature of the IR spectra. The position of the symmetry of the molecule also influences the position of the stretching carbonyl frequency. Now, the number of bands as well as their depths, it also is influenced by the medium in which the IR is taken. So here, if we take a solid IR or we take a liquid IR, then that is also is influences the IR, the position of the CO, stretching frequency, or the position of the peak in the IR pellet. So when the medium is in solid phase, that is when we take the KBr. KBr is the potassium bromide that is mixed with our sample to take the solid KBr of our sample. Then intermolecular vibrational coupling here takes place. So to avoid some sort of distortion, then mostly the metal carbonyl, they are taken in dissolved in hexane, or we take the vapor phase IR. The spectral changes, they may be observed for cases when the phase change from solid to solution, like for example CO to CO8. We will study, suppose for eta 5, that is FeCO CO2, when it is in solid phase it has C2H symmetry, but due to intermolecular coupling there is splitting of the single band for terminal and another single band for bridging CO. So if we take again this in solution phase, then the terminal CO, it again splits into two other bands. So that is why it exists in three isomeric forms, that is cis, trans, and the open form. The cis trans isomers, they show one type of IR, whereas the open form, it shows the other type of IR. So what happens is, at equilibrium the cis and trans isomers are predominant. Here the cis trans and the open form, they has been shown. Now looking into the arrangement or the symmetry of these molecules, so we observe different types of IR peaks or the stretching frequencies in the IR spectrum. Then coming to CO stretching frequencies and the force constant. So what are these force constant? We know that if a molecule undergoes distortion, then there has to be some other motion which will counteract this distortion. So the bond order here, we know it is only relevant to the stretching force constant. So here, what is this CO stretching frequency with bond order? So first we will, to understand this, we will look into some of the examples. As the electronegativity of R increases for the complexes RMnCO5, then the CO stretching frequencies often increases. Suppose we have CF3MnCO5, the observed frequencies are 2134, 2109, and 2043. Yes, if we take CH3 MnCO5, then the frequency, it gets reduced to 2111, 1990, and 2012. So that is why if we change just the ligand from CF3 to CH3, then the CO stretching frequency, it also changes. So also we should know that the type of metals that are forming the complexes. So when we take molybdenum or oxygen of the CO of this BF3 attack here in this molecule, that is shown in figure 2.23, then the symmetry of the resulting molecule, it is changed, and the electron density is also changed. So as a result, so what happens here is, we see a change in the IR stretching frequency. So let us examine a ligand metal, that is sigma and pi effects of the formula LmCO5. That is, here it is shown in figure 2.4. Here L is the organic group, M is the metal, CO is the ligands. That is CF3, for example, it is CF3MnCO5. So here the cis ligands, they have only one metal pi orbital for interaction, but the trans form, it can utilize the two metal d pi orbitals. So because the cis transformation and the symmetry are different, so that is why the stretching frequency is also different. Then metal-metal bonds, they can be predicted easily with the help of the 18 electron rule. But we cannot distinguish between bridging and terminal ligands because both the electron counts remain the same. The probable bondings of symmetric and semi-bridging carbonyls, they, with and without bonding, here it has been shown. So what is this semi-bridging carbonyls? Semi-bridging carbonyl means that the CO ligands are unequally shared between two metals. Then tetranuclear osmium complexes like OS4, CO16, they have been prepared. So tetranuclear osmium complexes, they have been prepared like OS4CO16, and we see that it is consistent with 456 metal bonds. Here in figure 5.26, you can see that the probable bondings of symmetric and semi-bridging carbonyls, they have been shown. The structures of this tetranuclear osmium complexes, it has been shown here. So here OS4CO15, it is weakly semi-bridging. So semi-bridging means that the CO is unequally distributed. So here it and all CO ligands are fully non-bridged in the puckered OS4, which this is considered as the metal carbonyl analog of cyclobutane. So here we were talking about tetraosmonyl complexes. So we will talk about CO2, CO8 that exists in solution. So both the bridged and non-bridged forms of CO2, CO8, they exist in solution. This shows that the energy difference between the two isomers is very less. The steric factors, they may be the prominent reason deciding whether the carbonyl ligands, they would bridge or not. These are the two plots that has been shown here. So in summary, so this is the different types of metal carbonyls, the EAN rule that has been discussed here. So some of the terminal questions has been along with their answers that is listed here. So with this, the metal carbonyl part is over. We will start with the metal pi complexes. So metal pi complexes, we talked about this is an important area of metal ligand chemistry. The covalent bonding, we understand it takes place between atoms which have almost the same electronegativity. So it means that most transition metals, they have the same, nearly the similar electronegativity, like that of boron, carbon, or elements below nitrogen, as well as sometimes below that of oxygen. So large number of compounds have been prepared involving bonds between transition metals and one or many of these elements, particularly carbon. So therefore, based on these facts, organometallics have been divided into three classes based on the type of bonding that is present between the carbon and metal atoms. The first one, it is called as the metal alkyl or metal aryls. So here in this case, the metal carbon bond is just a conventional electron pair, but it is sigma bond. Then the second group is the uh, metal carbon bonds, where the ligand molecules, they serve both as a sigma donor and a pi acceptor. That is the CO and PR3, they are compounds in this type of group. The third type is where the ligands, they serve as a pi acceptor, as CO it does in some type of compounds. So here the electrons donated by the ligands, they are not sigma non-bonding, but they are pi bonding. So here the ligand, it serves as a pi acceptor also, as well as a sigma donor. There is very little electron transfer, and hence the bonding is essentially covalent. Bonds of this type, they are formed by not only isolated double bonds in olefins, but also by extended pi systems. Therefore, a simple organic ligand, it can donate 2, 3, 4, 5 ligands from the pi systems. So depending on the number of pi donors, 1, 2, 3, 4, 5, 6, many classes of these metal pi complexes, they can be formed. So starting with transition metal nitrosyl complexes. So in this section, we'll talk about nitrogen monoxide, that is the NO. It is an odd electron molecule. nitrogen has 5 and oxygen has 6. So that is total 11, and hence it is called as an odd electron molecule. So then we will look into the molecular orbital diagram of nitrogen. So this is the atomic orbital for nitrogen, and the right hand side is the atomic orbital for oxygen. So in between we can see is the molecular orbital for NO. And interesting part here is that if we look into the pi star 2px, there is an unpaired electron. Since there is an unpaired electron, this NO is mostly paramagnetic in nature. So here, and the NO, it readily gets oxidized to NO plus cation, which is isoelectronic with N2, and it has a bond order of 3. So that implies that it is a N triple bond O. So therefore the bonding molecular orbitals of the NO molecule, they are more or like the similar like the oxygen atomic orbitals, whereas the antibonding molecular orbitals, they are more like the nitrogen atomic orbitals. So if the NO radical, it is bound to a metal, then we call it as the nitrosyl ligand. If the electron pair, it can occupy the low-lying metal-based molecular orbital, which are non-bonding, then the nitrogen, it can function as a sp sigma donor with synergic pi back bonding. So similarly, more or less, this nitrosyl ligand, it behaves similar to that of carbonyl ligands. But here the metal is electron poor system. But if the metal is an electron rich system, then the pair of electrons, it resides on the non-bonding orbital and allows the lower lying orbitals to be fulfilled. Thus, when nitrosyl ligand, it results because of this type of property, it results in a bent system. So, nitrosyl ligand, when linear, it is a 3 electron donor, and bent nitrosyl is a 1 electron donor. So, we see this possibility was not there for carbonyl ligand. So, but nitrosyl ligand, there are two possibilities. If it is linear, then it can contribute 3 electron donor. It is a 3 electron it can contribute. But when nitrosyl is present in a bent type of system, the number of electrons it can contribute is 1. So in the oxidation state of the method, both forms are 2 electron donor. That is why we will NO plus linear NO, it behaves as a coordinated nitrosyl ion, and the bent form, it behaves as a coordinated NO minus ion. The free NO, it exists as a stable free radical due to the weakness of the ON-NO bond in the dimer. So an alternative to use free NO for the synthesis of nitrosyl complexes. So here it is isoelectronic with CO, and hence it can be used in place of CO for a substitution reaction. So we can mentally construct NO from CO by adding an extra proton, that is, and a neutron to the carbon nucleus to give us NO plus, and a single electron to the pi star orbital to account for the extra valence electron of NO versus C. Now NO ligand can coordinate in different modes in their metal complexes. This is the linear form, this is the bent form that is shown in figure B, and this is the bridging form. So the NO can form complexes in 3 different types of coordination forms. The conversion of linear to bent MO, this leads to an increase in the oxidation state by 2 units. So once the electron density on the metal is increased, then the linear to bent conversion is promoted. It becomes easier. Like for example, here this is the covalent model. As you can see, this is the linear. But to form the bent type, then there is a promotion of the electron rich density. Of the electron density, it should be increased for the metal atom. So an example of a bent nitrosyl group here in figure 6.4, it has been shown for the part A1, it is called as the Vasquez derivative. In equation 6.1, it has been shown. This Vasquez derivative, it is an example of a bent nitrosyl compound where the NO, it is present in bent form. So the geometry of the product, it is square pyramidal with a bent nitrosyl. Here it has been shown in like this. This is a Vasquez derivative, and it is a here the NO here it is in bent form. Both linear and bent nitrosyls they are present here, and this here is an example of a linear nitrosyl that has been shown in figure 6.4b. So now coming to transition metal dinitrogen and dioxygen complexes. So the molecular dinitrogen, that is N2. Here we know it is isoelectronic with both CO and NO plus. So although the number of complexes with CO and NO plus are there, dinitrogen complexes they are difficult to form. Although they are same, dinitrogen when we talk of particularly N2, the complexes are very rarely found. Dinitrogen is a weaker sigma donor as well as a weaker pi acceptor than CO. So that is why the binding is very strong. Only good pi donors they form these N2 dinitrogen complexes. Like in equation 1, it shows the reduction of this ruthenium compound to form the dinitrogen complex. Here in the final product here it is shown in equation 6.18. It shows RuNH35N2. So that is here dinitrogen. Here it is formed, and this is the first example of a transition metal dinitrogen complex. The dinitrogen is a strong nucleophile which is shown by its displacement of water. Here it is shown in equation 6.9, and by the formation of a bridged complex. Here it is shown in equation 6.19. So this is how it is formed. The two metal atoms they may be bridged by the dinitrogen molecule in this way. This is the dinitrogen molecule. So this is how, this is one method of the arrangement. But if there is a back bonding, then this type of arrangement is also possible. In the first case, it is Mn, and N there is triple bond N and followed by the attachment with the metal bond. But here, if there is the back bonding, then the arrangement becomes M double bond N and there is N single bond. So this is the back bonding which reforming to the bridging N2 in the dinitrogen complexes. So majority of the complexes they have this monohapto N2 where bonding is similar to that of the isoelectronic co-ligand, that is mostly in figure 6.16. Sometimes these dinitro ligands they also bind in the Sidon mode here as it is shown here. So this is a dihapto and here it is shown here. So the IR stretching band of dinitro ligand, dinitrogen ligand, here it is in the range of 2150 to 1990. Haber-Bosch was the process was the first where dinitrogen that we know this is a process for manufacture of ammonia where N2 it was adsorbed as nitrogen atoms on iron catalyst at high temperature and pressure. So this is the first example. Most of the transition metals they have been used to prepare N2 complexes, and a lot of research has been done to it to understand its coordination ability. Then the unshaded region here, the dinitrogen based complexes have been synthesized with various types of metal atoms. Here it has been shown in figure 6.1, the table. The unshaded region shows the elements which forms mononuclear dinitrogen complexes. So if we look here, we see that those metal ions which form mononuclear nitrogen complexes, they also form carbonyls. This indicates that bonding of dinitrogen and carbonyl are similar. Also from this table, we see that the elements Fe and Mo, like here Fe and here iron is here and Mo, so they form both dinitrogen complexes and carbonyls. So in figure 6.9a, the complex CO N2PPH3, here it is shown. This is a representation of cobalt dinitrogen complex. This is the first example of the transition metal dinitrogen complex that was prepared directly from gaseous N2. In figure 6.9b, this is the first example of a molybdenum dinitrogen complex. You can see the molybdenum is here and here MPPH whole 2 and this is N2. So here N2L2, this is the first molybdenum nitrogen complexes. So in a nitrogen metal complex, other ligands such as phosphines, halides, hydride, ammonia, carbon monoxide, they can also be present. We know the nitrogen fixing bacteria, that captures atmospheric nitrogen, that is also they contain active sites of iron and molybdenum, and then they used for to maintain the nitrogen cycle in the atmosphere. So many Fe and Mo complexes have been used by taking the example of nitrogen fixing bacteria and looking into their coordination ability. So now we will look into the method of preparation of N2 complexes. So first is by direct using gaseous nitrogen. So this provides how the various complexes they have been used, like CON2 whole 3, RuH2N2 whole 3. They have been just prepared by taking the ruthenium or the cobalt complex and directly passing nitrogen, gaseous nitrogen over it. Then there are other compounds that have been derivated and synthesized in ether. So here if we take titanosine dimer and we expose it to N2 in ether, then we see the titanosine dimer N2 complexes. Isopropyl magnesium chloride and FeCl3 they react under N2 to form the complex. So Grignard reagent have also been used to prepare N2 complexes of molybdenum. Also in the presence of tertiary phosphine, so COCH13C6H12, it will react with nitrogen to form the complex. Then zinc dust, in the presence of excess phosphine and dinitrogen in THF, it also forms the complexes. Molybdenum, these are some of the examples, like molybdenum acetyl acetonate also reacts with nitrogen in toluene to form the complex. Then preparation of compounds that contains preparation of the nitrogen compound from compound which contain chains of nitrogen atom. Suppose we take oxidation of the coordinated hydrazine. Here this is the coordinated hydrazine, and the oxidation is done in presence of H2O2 hydrogen peroxide in THF, then the dinitrogen complex is formed. So it has also been found to prepare the ruthenium complex. Here with we will react it with an azide N3 minus in pH 4, and it forms the ruthenium dinitrogen complex. So the third method of preparation is in which the nitrogen atoms they combine to give the nitrogen complex. So here in this reaction, this osmium complex it's react with HNO2. So this is only successful for osmium and no other reactions is possible. So an intermediate amide complex is found in the reaction that is shown for PPH3 ruthenium complex, and it is thus only possible for the ruthenium amide complex. Then transition metal dioxygen complexes. So for the molecular orbital theory, the paramagnetic behavior we know of dioxygen is explained. We all know that oxygen O2 can be written in this form, and this explains the paramagnetic behavior of dioxygen. So the antibonding molecular orbitals of O2 they are half filled. So this superoxide O2 it results by addition of one electron which converts it to O2 2 minus. So the bond order and bond distance for different oxygen species it has been shown here. So some common bonding modes of oxygen in metal complexes they mostly occur through superoxo or peroxo. So like in myoglobin or hemoglobin, the binding involves the transfer of an electron from the metal to the O2, resulting in the superoxide anion here as it is shown in this figure. So in dioxygen coordination complexes, the Sidon mode is seen. This mode is often seen in Vaska's complex. Here the Sidon of the O2, here it has, this is the complex, this is the Sidon of O2, it has been shown here. So the examples of other metal complexes here, they have been shown for different dioxygen complexes. So most of the transition metal ions, they have oxidation states ranging from 2 to 6, they bind with dioxygen. For example, hemoglobin and myoglobin. These are some naturally occurring proteins, and we know that they bind with oxygen and they are found in the red blood cells of our body. We know the hemoglobin, it contains an iron center with four porphyrin rings that are attached to it. So this binds to the dioxygen and it helps in maintaining the oxygen content or the respiration of our body. Then Vasquez complex is a trans chlorocarbonyl bis triphenyl phosphine iridium. So here it is a square planar complex and it reversibly binds to dioxygen, and thus the here the color changes. The original color is yellow. After the oxidation, here it changes to orange color. Then hemocyanin, these are certain molecules, they are enzymes, copper containing metalloenzymes, they are called as hemocyanin. So when we have deoxyhemocyanin, that is after there is oxygen is removed, then the deoxyhemocyanin is colorless in nature, but when it binds with a dioxygen molecule, then the color changes to blue. And the best method to synthesize dimetal dioxygen complexes is just to expose the metal complexes to gaseous oxygen. So for this we can use dioxygen saturated solvents, or mostly what happens is oxygen is bubbled through the metal solution. So once you bubble the oxygen through the metal solution, then they are the dioxygen complexes was formed. So here one example, it has been shown here for rhodium complex. This reaction was done when we take a rhodium precursor and directly oxygen was passed through it at 3 atm pressure, and then a dark color complex was formed, which is here, it is shown in figure 6.35. So this is just how can we prepare the common dioxygen complexes. The other routes also involved, they can be from synthesis from superoxide or peroxide. These are less commonly used. The more commonly used processes that involves the passing of the dioxygen into the complexes. So this is all about your dioxygen and nitrogen complexes. So then coming to tertiary phosphine. So phosphine, we know it is a PPH3 ligand. So the phosphine complexes, we know they do not have, since it is PPH3, they do not have a direct metal to carbon bond. So that is why they are not considered organometallic in nature. But their bonding have lot of similarities with that of carbon monoxide. So that is why they are also considered as a special class of organometallic compounds. The substituted phosphines like the PR3, PR2AR or PAR3, they are these molecules, they are widely used. These tertiary phosphines are one of those rare ligands where the electronic and steric properties can just be varied if we change the R group. So the trialkyl or the triaryl phosphines are also possible. Mixed haloalkyl, haloaryl phosphine compounds, they are also possible. So the sigma donor ability and the pi acidity of the phosphines, they are similar to that of the carbonyls. The substituted phosphines, they are well bridged, multidentate, and here the multidentate di and triphosphines, like for example PH2P, CH2, CH2P, PH2. Here it is called as DPPE, that is di and triphosphines. They are and they are loosely referred to called as phosphine. Here it is structure of DPPE. Here it has been shown. How? So the phosphine, it contains a lone pair on the p atom and it forms 4 sigma bond from ligand to d metal atom and pi bond metal from metal to ligand like the CO. So here in 6.6, the sigma bond from ligand to d metal and pi bond from metal to ligand, here it for phosphine, it has been shown here. Even this structure has been confirmed from molecular modeling software. So C.A. Tolman, he introduced a pictorial semi-qualitative treatment to it. So by establishing establishing the treatment of the actual structure of the phosphine, the extent to which different ligands are oriented in space and to each other, it can be estimated by knowing the size of the cone. So here is the cone, ligand cone angles, which, and then we can assume the position of the ligands. So following is the order of the increasing pi acid character. But here this cone angle theta, this is, although it is rough, but it has been useful for knowing the, we call it the Tolman cone angles. So here it has been for different type of phosphine, the cone angle has been shown. Now, regarding the pi donor and pi acceptor properties, it is found that as the average electronegativity of the three groups attached to the p increases, the ligand becomes poorer sigma donor but a better pi acceptor. So, the pi donating ability of the phosphines, it is inversely proportional to its pi acceptor ability. So, we should remember that the electron rich phosphines, they are good sigma donors and poor pi acceptors, but the electron poor phosphines, they are poor sigma donors and good pi acceptors. Then these are will, this much is for today. In tomorrow class, we will talk about different types of the phosphine, monophosphine, diphosphine, and other phosphines. So we'll continue with this phosphine class tomorrow. So thank you for today.
Thank you, ma'am.